Most revolutions announce themselves loudly. The semiconductor did the opposite. It emerged quietly inside laboratories and research papers, hidden in components so small that most people would never see them. Yet, from that nearly invisible beginning came one of the most powerful technologies in human history. Semiconductors now sit at the center of modern life. They are inside phones, laptops, satellites, cars, medical devices, weapons systems, financial networks, cloud servers, and artificial intelligence. Entire industries depend on them. Governments compete over them. Economies rise on their production. A device smaller than a fingernail can shape the balance of global power. But none of that was obvious at the start. The semiconductor began as a scientific puzzle, a strange category of material that behaved unlike the conductors and insulators scientists already understood. Over time, that puzzle became a breakthrough. That breakthrough became an industry. And that industry became the hidden infrastructure of the digital world. This is the history of semiconductors, from lab discovery to global power. To understand semiconductors, we have to go back to a time before computers, before Silicon Valley, and before the modern electronics industry existed at all. In the 19th century and early 20th century, scientists were trying to understand how electricity moved through matter. Some materials, like copper, let electric current flow easily. Others, like rubber and glass, resisted it. But there was another class of materials that did something more complicated. These materials did not always conduct electricity well, but they did not block it completely either. Their behavior changed depending on temperature, impurities, and other conditions. They seemed to occupy a middle ground. That is why they came to be called semiconductors. At first, this was mostly a matter of scientific curiosity. Researchers knew that certain crystals could be useful in early electrical devices, especially radios, because they could guide electric current in one direction more easily than another. But the deeper significance of this behavior was not yet clear. Semiconductors were interesting, but not yet world-changing. The real transformation required a deeper understanding of physics. As scientists learned more about the structure of atoms, electrons, and solid materials, they began to understand why semiconductors behaved the way they did. Materials like silicon and germanium had electrical properties that could be altered in precise ways. By adding tiny amounts of other elements, a process known as doping, scientists could change how electrons moved through the material. That discovery was one of the keys to the future. It meant that electrical behavior could be designed. Once a material can be engineered, it can become a technology. And once a technology can be reproduced reliably, it can become an industry. For much of the early 20th century, however, electronics depended less on semiconductors and more on vacuum tubes. Vacuum tubes made possible radio broadcasting, long-distance communication, and some of the earliest electronic computers. They were the core of modern electronics for a time, but they had serious limitations. They were bulky, fragile, hot, and inefficient. Machines built from vacuum tubes could be powerful by the standards of their age, but they were also large, temperamental, and expensive to maintain. This created a growing demand for something better. Engineers wanted components that were smaller, more durable, more energy efficient, and more reliable. They wanted devices that could switch and amplify signals without the constant weaknesses of vacuum tubes. That need set the stage for one of the most important inventions of the 20th century, the transistor. In the late 1940s, researchers at Bell Labs developed the first practical transistor. This was not just another incremental improvement in electronics. It was a turning point. The transistor could do key jobs that vacuum tubes had done, but in a much smaller and more efficient form. It consumed less power, it generated less heat, it was far more durable. And perhaps most importantly, it pointed toward a future in which electronic devices could shrink dramatically while becoming more powerful. That mattered far beyond the laboratory. The transistor was not just a better part. It was the beginning of a different technological age. At first, transistors were expensive and difficult to produce. They were used in areas where performance justified their cost. Military systems, communications equipment, and high-end electronics all saw their potential early. But over time, manufacturing improved. Costs fell. Reliability increased. And transistors began spreading into more and more devices. This was the beginning of miniaturization. Radios became smaller and more portable. Electronic systems became more dependable. Designers gained new freedom. Devices no longer had to be built around the limitations of vacuum tubes. The transistor gave engineers room to imagine a future of compact electronics. And once that future became visible, it became difficult to stop. But even the transistor did not solve everything. As electronic systems became more complex, another problem emerged. Engineers could now build smaller components, but advanced machines still required enormous numbers of those components to be connected together. The more complicated the device, the more difficult the wiring became. A machine might contain thousands of individual parts, each one needing to be linked correctly. This made electronics expensive, time-consuming, and vulnerable to failure. The next great leap came from solving that problem. Instead of making each transistor separately and connecting them one by one, engineers developed a way to place multiple components onto a single piece of semiconductor material. This was the integrated circuit, and it changed the history of technology. The integrated circuit did not merely improve electronics, it reorganized the entire logic of the industry. By putting many components together on one chip, it reduced size, improved speed, lowered cost, and increased reliability all at once. Something that had once required a complicated assembly of separate parts could now be built into a compact, integrated structure. This was revolutionary because it opened the door to scale. Electronics could now be made smaller not just once, but repeatedly. Complex systems could be shrunk, standardized, and mass-produced. The integrated circuit was the bridge between the age of electronic invention and the age of electronic infrastructure. From there, the pace accelerated. As engineers improved chip design and manufacturing techniques, more and more transistors could be placed onto a single chip. That meant more computing power in less space. Over time, this trend became one of the defining patterns of the modern world. It was famously described through Moore's law, the observation that the number of transistors on a chip tended to rise dramatically over time, while costs per function fell. Whether treated as a scientific law or an industrial goal, the effect was enormous. For decades, the semiconductor industry lived by the expectation that chips would keep getting smaller, denser, cheaper, and faster. And for a remarkable span of time, they did. That steady advance helped transform computers from rare, room-sized machines into tools that could sit on desks, then in briefcases, then in pockets. It helped make possible calculators, digital watches, video game consoles, mobile phones, navigation systems, medical instruments, and eventually the vast ecosystem of connected devices that defines the present. The history of semiconductors is therefore inseparable from the history of modern computing. You cannot understand one without the other. When microprocessors arrived, the change became even more dramatic. A microprocessor placed the central processing functions of a computer onto a single chip. This made computing far more compact and far more accessible. It helped create the personal computer revolution. Once computing power could be concentrated on inexpensive chips, computers no longer needed to remain the property of governments, research institutions, and giant corporations. They could become personal devices. That shift changed culture as much as technology. When people talk about the digital age, they often think first of the internet, software, or smartphones. But beneath all of those developments lies semiconductor technology. Without the chip, there is no practical modern computer. Without the chip, there is no affordable consumer electronics market. Without the chip, there is no digital world in the form we know it. That is one of the defining features of semiconductor history. The technology is foundational, yet often invisible. Most people interact constantly with devices powered by chips while rarely thinking about the chips themselves. The semiconductor disappears into the product. It becomes part of the background of daily life. And yet the less visible it becomes, the more essential it often is. The rise of semiconductors also transformed geography. In popular memory, the industry is closely linked with California, especially Silicon Valley. That connection is real. Silicon Valley became a major center for chip innovation, electronics entrepreneurship, and venture capital. It helped shape the modern technology economy. Many of the companies and ideas that defined the late 20th century grew from this environment. But semiconductors did not remain a local story for long. The industry grew into a global system. As chips became harder and more expensive to produce, different regions began to specialize in different parts of the semiconductor supply chain. Some focused on design, some focused on fabrication. Some specialized in equipment, materials, packaging, or testing. Over time, the chip industry became one of the most globally interconnected and technically demanding sectors in the world. A semiconductor might be designed in one country, manufactured in another, packaged in a third, and assembled into a final device somewhere else entirely. This model helped the industry become more efficient, but it also made it more fragile. The system worked brilliantly when trade flowed smoothly and supply chains remained stable. It became much more complicated when disruption appeared. That fragility became visible whenever shortages struck. Consumers often saw only delayed products or higher prices, but the deeper lesson was much larger. A shortage of chips could slow automobile production, delay consumer electronics, disrupt industrial machinery, and affect everything from appliances to medical equipment. Tiny components, almost invisible to the average buyer, could hold up entire sectors of the global economy. That is when many people began to understand what semiconductors really were. Not just parts, but infrastructure. The complexity of semiconductor production is one reason they became so strategically important. Manufacturing advanced chips is among the most difficult industrial tasks ever attempted. It requires extraordinary precision, ultra-clean facilities, advanced chemicals, world-class engineering talent, and billions of dollars in capital investment. The most advanced fabrication plants are not ordinary factories. They are technological ecosystems of extreme complexity. This creates concentration. Not every nation can build advanced chips. Not every company can compete at the leading edge. Over time, capability gathered around a relatively small number of firms and regions that possessed the skills, tools, and investment required to stay ahead. And that is where the history of semiconductors becomes a story of power. By the late 20th century, and even more clearly in the 21st, governments began to recognize that chips were not just commercial goods. They were strategic assets. Semiconductors mattered for defense systems, communications networks, aerospace, intelligence, finance, artificial intelligence, and industrial productivity. Control over semiconductor technology meant influence over the systems that increasingly governed modern life. In an earlier age, oil was often seen as the critical resource of power. In the digital era, semiconductors became something different, but equally vital. Oil powered engines and transportation. Chips power computation, communication, coordination, and increasingly decision-making systems. They do not simply fuel economies, they organize them. This shift turned the semiconductor industry into a geopolitical arena. Questions that once seemed technical became political. Who controls advanced manufacturing? Who has access to the most sophisticated equipment? Which countries dominate design? Which nations can secure supply chains during crises? Which companies can build the chips required for next-generation computing and artificial intelligence? These are not narrow industrial questions anymore. They are questions about national power. The rise of artificial intelligence has only intensified this reality. Modern AI systems require massive computing power, and computing power depends on advanced chips. The same is true for cloud infrastructure, high-performance computing, autonomous systems, military technologies, and many of the industries expected to define the future. The semiconductor is no longer just one part of the economy. It is the condition beneath many of the most important technologies of our time. That helps explain why semiconductors now appear in political speeches, economic planning, and diplomatic strategy. Research funding, export controls, industrial policy, and domestic manufacturing initiatives all reflect the same understanding. Whoever leads in chips gains leverage across many other fields. But even that is only part of the story. The history of semiconductors is also a story about how modern life became compressed into the microscopic. Each generation of chips packed more capability into less physical space. As a result, everyday devices became more powerful while appearing simpler. Phones replaced cameras, maps, calendars, music players, and much more, because so much computing power could fit into a handheld device. Cars became computers on wheels. Homes filled with smart systems. Cloud platforms connected people across continents in real time. The semiconductor made all of this possible not through spectacle, but through repetition and refinement. Layer by layer, generation by generation, engineers pushed performance higher and size lower. The public often noticed the products. The chip itself remained behind the curtain. That invisibility can make the semiconductor seem less historical than it really is. We tend to remember rockets, skyscrapers, and famous consumer products because they are visible symbols of change. Chips are harder to see, so their revolution feels quieter. But in terms of long-term impact, semiconductors belong among the most consequential technologies ever developed. They reshaped communication, warfare, commerce, medicine, education, entertainment, and science. They accelerated globalization while also exposing its vulnerabilities. They changed how humans work, how governments operate, and how information moves through society. They also changed time itself, at least in a practical sense. By enabling faster computation and communication, semiconductors compressed the speed of business, media, logistics, and decision-making. They helped create a world in which information could be processed instantly, and action could follow almost as quickly. The rhythms of modern life became inseparable from the capabilities of the chip. And yet, despite all this, the future of semiconductors is not simple. For decades, the industry advanced through relentless miniaturization. But the smaller components become, the more difficult it is to keep shrinking them. Physical limits, engineering challenges, energy demands, and production costs all place pressure on the old model of progress. That does not mean semiconductor history is ending. It means the next chapter may look different. Instead of relying only on smaller transistors, the future may depend on new materials, new chip architectures, advanced packaging, specialized processors, and more efficient ways to distribute computing tasks. The era ahead may be defined not by one single path of progress, but by multiple strategies at once. Some chips will be designed for artificial intelligence, others for energy efficiency, others for edge devices, sensors, networking, or specialized industrial functions. In other words, the future of semiconductors may be about diversity rather than uniformity. But the core reality remains the same. The world will demand more computing, not less. More data, more automation, more connectivity, more intelligence built into devices, systems, and infrastructure. All of that depends on semiconductors. That is why the history of semiconductors matters so much. It is not merely the story of one material or one industry. It is the story of how scientific research becomes technological capability, how capability becomes economic strength, and how economic strength becomes geopolitical influence. It is also a reminder that the forces that shape history are not always the most visible ones. Sometimes the technologies that matter most are the ones hidden inside everything else. From the early study of strange electrical materials to the invention of the transistor, from the integrated circuit to the microprocessor, from local innovation to global supply chains, semiconductors have moved from scientific curiosity to industrial necessity to strategic power. They began as a puzzle in physics. They became the foundation of electronics. They became the engine of the digital age. And now they stand at the center of the modern world. That is the paradox of the semiconductor. It is tiny, but it scales into everything. It is technical, but it shapes politics. It is hidden, but it helps define the visible world. From lab discovery to global power, the rise of semiconductors is one of the great stories of modern history. And like the technology itself, its influence is still expanding.